Oh, hey, Professor, quick question.
Yeah.
Are these lecture slides that you're about to show going to be on iLearn?
So good question. And they're actually on my public website. It's gonna take you probably a couple days to see where are things on the public website or on iLearn. And I kind of historically have used my public website, so it's kind of like um, yeah. So I a lot. Short answer is it's on the public website. So the website link is on iLearn, and you can get there from iLearn. But yeah, since there's a lot of material in this course, I think there's kind of like a logical separation that I use, and I put all the assigned reading and homework problems, and also the lectures, the PDF copies of these lecture notes. They're on the public website, not on iLearn. So just take a look at that website. You'll get in the groove pretty quickly. All right.
Got it. Thank you.
Okay. So let's see. So you guys you see my PowerPoint now, right? I think. Yep. Cool. All right. So chapter 1. Let me just check one more thing. Sorry. Chapter 1 of your organic chemistry experience. So yeah, this is not a PowerPoint course like the way a lot of courses just are PowerPoint. First couple chapters will be PowerPoint though. And I think it just makes sense. When we're reviewing Gen Chem, we don't necessarily need, one sec. It makes sense to cover certain topics like general chemistry topics through sort of PowerPoint format. Okay. All right. So what are the things we're going to talk about? Structure and bonding of organic molecules. We're going to introduce kind of structure and bonding, talk about Coulombic forces, Ionic and Covalent Bonds, Electron-dot models of bonding. So this is all stuff you should kind of know from Gen Chem already. Resonance forms, that's a big one. You're going to be using resonance throughout Organic 1 and Organic 2. So that's going to be a big topic, okay? Atomic orbitals, we're going to cover kind of the orbital structure in atoms, and a little bit on molecular orbital theory and covalent bonding. Molecular orbitals and molecular orbital theory is a big can of worms. There's a lot to learn there, and but that'll be probably deferred mostly to your physical chemistry course if you take that later. So you'll learn the basic idea of molecular orbitals, and definitely covalent bonding is a big one because most of the bonds in organic chemistry are covalent. Hybrid orbitals and hybridization, that's a big one too from this chapter. We got to identify hybridization in organic molecules. That'll probably be in one of the quizzes. I would say each of these, resonance, hybrid orbitals, and hybridization, and in really drying molecules, all of these are going to be kind of crucial sort of early quiz topics, okay? Okay, so first, what do I enjoy about organic chemistry? It provides a core understanding for a number of fascinating and highly relevant areas of study. There's a ton that you can do with organic chemistry. It's actually beyond like a stupid course you have to take to get your degree. There's actually a lot of people that use it to try to improve the world, right? And medicinal chemistry is what I do in my research. It's like I actually use organic chemistry as a tool to design molecules that can inhibit like a protein or enzyme or a channel protein or something that could be used to actually treat a disease. That's medicinal chemistry. I use organic chemistry in my research, not as my primary focus, but as a tool. Materials, so dyes, paints, fibers, polymers, plastics and things like that are all kind of a subdiscipline of organic chemistry. Biochemistry, pharmacology, neuroscience, they're all rooted in organic chemistry. Fuel chemistry, I think, is incredibly boring but you can make a ton of money studying fuel chemistry. You could work at like Chevron or somewhere, and there's a ton of money in it, doing kind of analysis and, you know, like trying to design optimal fuels, and there's a lot of analysis that goes along with that. And it's, but it is, you know, some people love that too. And so, but it's all organic chemistry, right? Okay, so a couple of your first organic molecules, aspirin, is you know, used as a mild painkiller. It's a series of carbons and hydrogens and oxygens. Teflon is a material, so it's kind of the second category. Teflon, and it looks a little weird with the parentheses in the N. Well, the N is like a large number, and so it's a polymer. So it's a bunch of repeating subunits. That's Teflon that's used in your nonstick coating of your frying pans, and also different kinds of like impact-resistant vests and things like that. GABA is a neurotransmitter, gamma-aminobutyric acid. So this is actually used in your brain as one of the ways to transmit information. Ethanol, of course, is a pretty simple molecule, CH3CH2OH. It's used as a fuel and also a solvent. And in our COVID-19 days, it's used as a disinfectant. Okay. Okay. So getting into bonding, chemical bonding. Coulombic forces are kind of one way to consider bonding. So bonds are made by simultaneous Coulombic attraction and electron exchange. So when two atoms approach, the electrons of one are attracted to the protons of the other. So this is one way that you can think about like bonding. It's kind of a simplified way to think about it. And there's an attractive force that's a constant, and then times the two charges divided by distance squared. The attractive force releases a certain amount of energy, and it's called the bond strength. And so that kind of gives the bond some, you know, energetic reason to exist. The optimal distance is called the bond length, and this kind of just shows the idea of this bonding model that there's like at a certain bond length, the energy is minimized, and if the atoms get closer, so the x-axis is the distance. As the atoms get closer to each other, it gets higher in energy, and if they get farther, it also gets higher energy. So it's optimal at this kind of low point, right? So there's an optimal balance between these two parameters. Okay. All right. Covalent bonds. Now let's talk about ionic and covalent bonds. Covalent bonds are based on the sharing of electrons, and you should know this from Gen Chem. If electrons are not equally shared, you'll have something called a polar covalent bond, which is almost like partially ionic, and but otherwise a purely covalent bond is formed. Okay, so here the idea is you have your two atoms, and they kind of approach, and then the electrons are shared, and that forms you know, the electrons are shared in the bond between the two atoms. Ionic bonds, of course, are based on the transfer of one or more electrons from one atom to the other. The resulting cation and anion are electrostatically attracted to each other. So things like salts and sodium chloride and things like that have this sort of configuration. So we might have two atoms, and one electron gets transferred to the other atom, and then you have one thing that's positively charged and one thing that's negatively charged, and they form this sort of like ionic bond. Think of NaCl or something, right? And the periodic table underlies the Octet Rule, which is going to dictate a lot of you know, the bonding we have in organic chemistry. Electrons occupy levels or shells of fixed capacity. If you look at the periodic table, the first shell has room for 2 electrons, the second is 8, or an octet, and that's going to be a lot of our organic chemical atoms will have 8 electrons around them. Carbon, nitrogen, oxygen, the halogens. Next row is we'll have 18 electrons. For the most part, though, we're going to be on the second row of the periodic table. Okay, and then noble gases have 8 valence electrons. Helium has 2, and are particularly stable. And so atoms like carbon or oxygen or nitrogen, they kind of want to achieve this noble gas configuration and have 8 electrons around them. Other elements lack octets in the outer shell, and they're and are driven to form molecules such a way to create a stable octet. Okay, so atoms like carbon again, or nitrogen or oxygen, will try to achieve this noble gas configuration and have 8 electrons around them. Okay, this kind of shows the partial periodic table, and for example, oxygen has 2 inner electrons and 6 valence electrons. So it'll try to get another 2 electrons, and it'll have 8 valence electrons on its outer shell. Kind of the way it'll try to achieve like what neon has, having 8 electrons in its outer shell. And you know, our main elements that we're going to consider are carbon, nitrogen, oxygen, fluorine. We'll also see chlorine and bromine. Okay. In a pure ionic bond, electron octets can be formed by transfer of electrons. So typical example is NaCl, sodium chloride. Okay. Alkali metals react with halogens. 1 electron is transferred, and then both atoms achieve a noble gas configuration. So NaCl, initially sodium has an extra electron, chlorine has an absence of an electron in its outer shell. And so 1 electron gets transferred from sodium to chlorine, and then now they're both in this noble gas configuration. And that's stable. That's why NaCl is a nice stable molecule. Okay, and this kind of shows it another way. So sodium initially has 1 extra electron. Chlorine has, well, sodium gives up its electron, and then chlorine has its noble gas configuration. You can calculate the energetics of this process. For sodium, to lose its electron, it's actually kind of endothermic. And so it actually is not favored. It's not favored for sodium to lose its electron. But then chlorine has electron affinity. So when it receives an electron, that's exothermic. We still have if we add these up, it's still a positive number. So that's disfavorable, right? Because the energy should be negative for it to be a spontaneous reaction. But then there's another term, the electrostatic attraction, for the 2 atoms to find each other and interact, and that's a -120. So it's a net exothermic attraction and net exothermic reaction. The delta E is -84 kilocalories per mole. So that's a very happy reaction for this to happen. It's actually explosive. When these 2 atoms find each other, it's a very, very extremely exothermic reaction, and can like a lot of energy released, and it's kind of a dangerous reaction. So almost uncontrolled reaction. Okay, so we can indicate the valence electron shell as electron dots. This is one of the ways we can draw molecules. We're going to get away from electron dot models just because there's much better ways to draw molecules. But this is a good start and a good review for general chemistry. So these are the valence electrons around like carbon, nitrogen, oxygen, and fluorine. And then when we show this electron transfer process, like Na dot losing its electron to give Cl a noble gas configuration, now we have Na plus and then Cl with 8 electrons around it, right? Magnesium can lose 2 electrons, and then ultimately you have two chlorines around it. So this is magnesium dichloride or magnesium chloride, okay? Hydrogen, there's 2 ways for hydrogen to kind of transfer its electrons. It can either gain an electron or it can lose an electron. If it loses an electron, it becomes a proton, right? H plus, bare nucleus. It has no electrons around it at all. And then hydrogen can actually gain an electron also. Then it becomes in its helium configuration. The proton is the more stable thing, and that's most of the time we see, proton in like HCl or like an acid or something. It is in its proton configuration. But we actually do see hydride also, H dot dot minus. Most likely you're going to forget the word hydride until about 8 chapters from now. until the end of organic 2, where we use hydride all the time as a chemical reagent to do chemical reactions, okay? But for the most part, yeah, you're used to seeing H lose a electron to become a proton. Okay, covalency. Covalency, so this idea of covalent bonds, which is very, very important in organic chemistry. In covalent bonds, electrons are shared to achieve an octet configuration. Ionic bonds between identical atoms do not form. So like chlorine, like if I have two Cls, they have the same electronegativity. Chlorine will never form an ionic bond with another chlorine. It'll form a covalent bond, right? So does a Cl-Cl form covalently or ionically? Well, it would not make sense that it would be ionic because they have equal electronegativity, right? So Cl-Cl is going to be a form of covalent bond. What's something that would form an ionic bond? Well, like Na plus Cl minus. Na plus is electropositive. Cl minus is electronegative, right? Okay. Carbon does not typically form ionic bonds with things. There's going to be a couple exceptions to that, but for the most part, carbon loves to form covalent bonds. So usually what carbon does is it gains 4 electrons and it enters the neon configuration, full octet, and it's bound to things. So for example, simple organic molecule is methane, right? CH4. So you can imagine 4 hydrogens around here, and carbon would be in its neon configuration. All right. Okay, so carbon typically achieves neon configuration and bonds covalently with things, 99% of the time. A couple examples of ionic and covalent bonds. So this kind of shows hydrogen, how 2 H dots would form a covalent bond to make H2. H dot and Cl form a covalent bond to make HCl. 2 chlorines would form both of them have full octets. Both of them have full octets. Cl2, right? In certain cases, one atom supplies both of the electrons in the bond. So ammonia, NH3, is a base, so it loves to react with protons. So ammonia, NH3, it actually has a full octet in its native configuration, but it will react with a proton and which has no electrons around it, and it'll form ammonium, NH4+. The charge will be positive. And then water, which also has a octet in its normal configuration, it can react with H+ and form hydronium, which is H3O+. Okay. Of course, the charges make sense here. We'll talk about charges in more depth in a second. But yeah, of course, neutral plus positive, what's the charge going to be in the product? Neutral plus positive will make something as positive. Neutral plus positive will make something as positive. And we'll review the rules for determining the charge in a second. So there's also these 4 electron, or we'll call them a double bond, and 6 electron, or a triple bond. These are a big deal in organic chemistry. We have whole chapters on this that you'll learn about later. I think chapter 11 and 12 are talking about double bonds, and 13 or something is the triple bonds. Okay. Yeah. So this is a double bond. This is a carbon double bond carbon. So we have 2. We have 2 atoms and they're double bonded. So there's 4 electrons total. So 2 electrons make one bond, 2 electrons make the second bond. So this is it's called ethene. More generally, we call these things alkenes, A-L-K-E-N-E-S. It's called an alkene, which is a double bond. And then a triple bond is when, and also remember that both carbons have a full octet, right? So this carbon has 1, 2, 3, 4, 5, 6, 7, 8. And this carbon also has 8 electrons. So both atoms have a full octet. And then the alkyne, or ethyne, which is a triple bond, So now both carbons have a triple bond between them because each pair of electrons is a single bond, right? So you got 3 single bonds, and that forms a triple bond between the 2 carbons. And this molecule is called ethyne. And these things more generally, as a group of compounds, are called alkenes, Alkenes, alkenes. And these molecules in general are called alkynes, Alkynes. And this will be a whole chapter or 2 in the book. And this will be a whole chapter or 2 in the book, alkenes and alkynes, okay? So polar covalent bonds, the electrons are not shared equally. So it's kind of in between the extremes of a pure covalent bond and a pure ionic bond, okay? So a lot of bonds in organic chemistry are polar covalent bonds. So it'll be a covalent bond that has sort of a polar component to it, or a polar property to it, okay? All right, so it's in between the 2 extremes of pure covalent and pure ionic. A lot of examples of this in organic chemistry. So many bonds will exist between these extremes. They're called polar covalent bonds. Each element has an electronegativity, which represents its electron accepting ability, how strongly it pulls the electrons, right? So you probably know about electronegativity from Gen Chem, right? So large difference in electronegativity will result in these kind of highly polar covalent bonds. This, hopefully you can see the colors. It kind of goes from sort of a bluish tint on the left, or sort of the electropositive atoms, and then on the top right and far right side are the more electronegative atoms. Fluorine being one of the more electronegative atoms. One of the more electronegative atoms, yeah. And the separation of charges results in the formation of a dipole. So when we have these atoms that are connected and differing electronegativities, there's going to be something called a dipole. We're going to represent this and show it when we draw a lot of molecules. One of the ways to do that is to draw an arrow towards the more electronegative atom, usually with a cross at the end of it. So these are a couple examples. So if I have a molecule A and molecule B, B is the electronegative one and A is the less electronegative one. We should have this sort of line with an arrow and a cross at the end of it. And this will, this is just a way to indicate the dipole, right? HF, great example, HF, right? So H is delta positive, F is delta negative. The dipole kind of goes towards the fluorine, right? Iodine monochloride. Chlorine is more electronegative. So we draw the arrow kind of in the direction of the chlorine, and we have the cross kind of in the positive direction. Fluoromethane. Yeah, question?
Yeah, I have a question. Oh,
Yeah.
sorry. I was always bad at this. How are we able to tell if it's a positive or negative charge?
So easiest way is you look at the periodic table, and things that are on the right are the negative ones, and things that are not, definitely things that are on the left, like a sodium way on the left is going to be positive. Carbon is kind of in the middle, and so relatively speaking, carbon is going to be delta positive. So it's when we say delta here, it means it's kind of like partial. It's not like it's not a full charge. It's a partial charge, right? So fluorine, though, if we look at the if we look at the last thing, I mean these numbers. The number is electronegativity, and you can see the fluorine is a big number. Carbon's not. It's electronegative, but it's not. It's kind of in the middle between like lithium and like fluorine, and that's yeah. And that makes sense. Okay.
That makes sense. Thank you.
Cool. And yeah, like when I think about carbon and I look at the periodic table, things to the right of carbon will be either partially electronegative or more extremely electronegative. So good reason to check out your periodic table again, right? Yeah, and methanol, simple molecule. Carbon, and both of these molecules have full octets around either the carbon or the fluorine, as you can see. Methanol is a full octet around carbon, and a full octet around oxygen. Oxygen's to the right of carbon on the periodic table. And so oxygen is kind of delta negative and the carbon's delta positive. So it's partial, carbon's partially positive, oxygen's partially negative. Hydrogen is on the left end of the periodic table, and it's kind of partially positive too, right? So we can kind of indicate the partial charges really using the periodic table, right? Okay. Then we have a molecule like CO2, right? Which the dipoles cancel each other. So the carbon is, we'll say, doubly delta positive. So the carbon is definitely delta positive. Both oxygens are delta negative, but there's a net canceling effect, right? This also shows this idea of it's called a electrostatic map, which is it sort of shows the kind of the electron. It's a computer-generated figure that shows the electronics of a molecule. And red indicates the presence of electrons, and the blue indicates the absence of electrons. So the carbon is kind of in the middle, and it's delta positive, and the oxygens are delta negative. Okay, cool. Hey, quick question. Do you guys see my mouse? I keep moving my mouse around.
Yeah, we can see your mouse.
Sweet. All right. I just want to make sure you can see my mouse. It's almost like my little laser pointer. Okay. Okay. So geometry of atoms. So what kind of geometry do atoms achieve? In most cases, the atoms want to be kind of as far apart as possible. That might be changed if there's like a lone pair of electrons. The electrons around a molecule or an atom will repulse from each other, and that defines the geometry using something called VSEPR method, valence shell electron pair repulsion method. And so we can usually figure out the geometry of things around a carbon or something. All right. So electron pairs arrange themselves to be as far apart as possible. In the case of two electron pairs, it'll be like a linear geometry. If we have three electron pairs, it'll be a trigonal geometry. We'll show examples in a second. If we have four electron pairs, it'll be tetrahedral. And that's like what we see most of the time in organic chemistry, like with methane or CH4. You have four electron pairs, they all repulse each other, and that's tetrahedral. Okay. So as an example of a linear geometry, beryllium difluoride is BeF2. So beryllium does not have a full octet around it, and that's because it's it actually, well, it can have a full octet, but it doesn't in this molecule. So it's not necessarily stable. But the point here is that the two fluorines around beryllium and the pairs of electrons will be as far apart as possible. And this is an example of a linear molecule. Okay, so the beryllium and the fluorines will be linear, not bent like you could possibly draw. Okay, BCl3, boron trichloride. This also does not have a full octet, and this happens to be a reactive molecule because it wants to achieve a full octet. It's just in this configuration, BCl3, it has 6 electrons around boron. But anyway, you can imagine the pairs of electrons separate away from each other, right? And this is an example of a trigonal geometry. So and there's a 120-degree bond angle between these different things. Not this kind of configuration where we just have like a empty site at the bottom. Okay, so it's going to be a trigonal geometry in BCl3. Organic molecules. These show a couple examples. This is what do we call it? It was a alkyne, right? The triple bond. So it's carbon, triple bond, carbon. The lines, each of the lines is a pair of electrons. So there's a pair of electrons there. There's 3 pairs of electrons here, so it's going to be 6 electrons total. You're going to get used to this. It might be uncomfortable initially, like seeing lines because you like drawing dots. But each line's a pair of electrons. So this is linear. Alkynes are linear. Alkenes are trigonal. Okay. So these kind of double bonded things are going to be trigonal. And so you have a pair of electrons, and then like two pairs of electrons, and it's going to be trigonal. And then like, you know, most of the molecules in organic chemistry are the sort of tetrahedral configuration. And these are four pairs of electrons represented by the different bonds. You may or may not know this, what the wedge means. Anybody know what the wedge means? This little wedge?
It means it's like pointing directly at you.
Outward.
Yeah, you got it. Yeah, the wedge. The wedge means it's pointing directly towards us. It's a three-dimensionality thing, right? So this H is coming towards us. The dash 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 is going away from us. Okay, and then the line to H going upward is just kind of in the plane of the computer's or screen, and the other one is also. So this just shows the tetrahedral geometry. Okay, and the dashes and wedges. That's going to be a really big thing in that stereochemistry chapter 5, I think it is, where we're going to be talking like crazy about all these dashes and wedges and three-dimensionality. Okay, and this is just a silly picture of tennis balls, kind of in a tetrahedral geometry also. Okay, electron-dot model of bonding. Talking a little bit more about organic chemical structure, the molecular skeleton, we want to talk about Lewis structures, which is one way to draw molecules. We're going to draw the molecular skeleton, connect the atoms, depict the covalent bonds with a pair of shared electrons, and give each atom a noble gas configuration. It's usually a full octet. Electronegative atoms may contain lone pairs as well. So this is a good way to draw, well, molecules. We have better ways to draw molecules, but this is like, as we're reviewing Gen Chem, you got to review Lewis structures. Okay, so here's an example of a correct Lewis structure: hydrogen bromide, HBr. So H has 2 electrons around it because it's above. It's a row 1 atom. Br has a full octet, so there's 8 electrons around it. Some incorrect ones. Put H with 3 electrons around it. That's not happy. And then also Br then would not have a full octet. So this is like an incorrect structure. The other thing is kind of forming a double bond between H and Br. Also, H doesn't like having 4 electrons around it. The other situation is like showing the wrong number of electrons around bromine. So it does not have a full octet. Okay. Here's a couple of organic molecules. Methane, of course, we've seen. Pretty simple. Ethane. Ethane is the same as methane, except it's got 2 carbons. So it's CH3, and the carbons both have full octets around them. Propane is kind of like ethane, but it's got an extra carbon. So it's CH3, CH2, CH3. We're going to learn all of the different, like, you know, if we start adding more carbons, it's like counting, like counting in a foreign language, which you're going to learn about methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane, undecane, dodecane. That's all going to be next chapter, where we start learning about kind of how to count in organic chemistry in terms of molecules. That's not today though. Ethanol. Ethanol, of course, is CH3CH2OH. Each of the atoms, carbons, and oxygens have a full octet. Ethane thiol may not have ever heard of before. It's the same thing, except it has sulfur instead of oxygen, and they look kind of similar. This stuff is insanely stinky. It's one of the stinkiest molecules you'll ever smell in your life. Thiols or SH, carbon SH, are incredibly stinky molecules. Bromoethane is 2 carbons with a bromine, and of course everything's got a full octet. These are all like these Lewis dot structures for these simple molecules. We talked about ethene or alkenes, and the double bond is represented as a 2 pairs of electrons. Ethyne, which is 3 pairs of electrons. This is a triple bond. So this is a double bond, this is a triple bond, yeah? And then nitrogen. Yeah, what are the geometries? We said this is trigonal, this is linear, and this is also going to be linear, okay? Yeah. Nitrogen is like N, triple bond N, right? Also, things like oxygen and sulfur and even bromine over here and nitrogen, they have bonding electrons and they also have lone pairs, right? Okay. Formal charges. So we need to determine the charge in molecules. We're going to introduce this and kind of continue next lecture. And I also have a much better way to do this, but this is a good review from your Gen Chem days. Formal charge is the number of valence electrons in the free neutral atom. We're going to subtract the number of lone pair electrons on the atom, lone pair, so non-bonding. We're going to subtract 1/2 of the covalent bonding electrons surrounding the atom. It sounds like a crazy formula, and we're going to do a way cooler way of doing this next lecture. But let's show a couple of these. Usually I show this on the board. This second I can't, and we're low on time. I'm going to have a way to kind of show you guys things on a little webcam probably by next time. But we'll just do these right now over Zoom. So oxygen here, hydronium. You should know this is positive, like H3O+, right? How do we confirm this? You know, oxygen is how many valence electrons? It's 6, right? It's the 6th column on the periodic table. So it's 6. It's valence electrons 6 minus the lone pair. There's 2. So 6 minus 2. And then 1/2 of the covalent bonding electrons. So 6 minus 2 minus 6 divided by 2 is 3. So 6 minus 2 minus 3. 6 minus 2 minus 3, it's positive, right? The hydronium is a positively charged thing. You should all know this. I hope. I usually look at people's faces and they're like either smiling or frowning, and I can't really do that right now, but you guys know this, right? Nitrosyl cation. Well, of course, the word cation is positive, right? Ionic things are positive. So nitrogen, it's 5 minus 2 minus 1/2 the bonding electrons. So 5 minus 2 minus 3. 5 minus 2 minus 3 is neutral. Nitrogen is neutral. And then oxygen is 6 minus 2 minus 3, right? 6 minus 2 minus 1/2 of the bonding. So that's positive. And of course, that makes sense with the word cation, right? Okay. Nitric acid. This oxygen, it'll be neutral. Nitrogen, let's do the nitrogen. Nitrogen is 5. There's no non-bonding electrons. So 5 minus 0 minus 1/2 of the bonding electrons. So it's 5 minus, we have 1, 2, 3, 4, 5, 6, 7, 8. So 5 minus 4. What's 5 minus 4? It's positive. So this is nitrogen is positive, right? This oxygen is 6 minus, we have 6 minus 4 minus 1/2 of the bonding electrons is 2. 6 minus 4 minus 2. 6 minus 4 minus 2 is neutral, right? And this one will be negative. So it's 6 minus 6 minus 1. 6 minus 6 is 0 minus 1, 1/2 the covalent bonding electrons. Okay. All right. I think we are done for today. We got a lot of cool stuff next time. And we'll continue these lectures. Okay. I guess I'm going to stop the recording. Let's see. Where's the stop recording?